Okay, this video is a quick example of how you would use Kirchhoff's loops and Kirchhoff laws in a problem. So you got a couple of batteries, 3 resistors. Notice that I can't reduce this circuit. Like R2, and R3 are not in series because there's a junction between them. And they're also not in parallel because this battery spoils it. For two things to be in parallel, they have to be the only two things in a loop. And in this case, R2 and R3 have to share their loop with the battery. So this is not a reducible circuit. Okay, so the idea in Kirchhoff loops is the first thing you got to do is pick a direction for every current. So in each branch, make up a current, give it a name, and then guess the direction of the current. If you guess wrong, it doesn't matter. The problem will still work out fine. You'll just end up with a minus sign in your answer. Okay, but each branch, every time you hit a node, you need a new current. So I start with I1. Here I have I2 and I3. And then you need to pick a direction to go around your loop in. So I'll go around both loops in the clockwise direction. I don't have to go in that direction. I could go counterclockwise, but normally you go clockwise. It doesn't really matter. You might also say, hey, how come you're choosing those two loops? Can't you go all the way around as one big loop as well? Absolutely, you can. In fact, you'll always have more loops than you need, and you'll end up writing redundant equations if you use them all. So I just like to use the little loops. It may turn out in a particular problem that it's easier to use the big loop, but I don't waste any time thinking about that stuff. I just use the little loops. Okay, so now we need to pick a point for each loop to start at. So A is our point. We'll go all the way around the loop until we get back to A. B is the point for this loop. We'll go all the way around the loop until we get back to B. Okay, and so now we actually can start to write stuff down. The first thing we want to write down is current conservation. And so what does that mean? Any current that flows into this node has to equal the current that flows out of the node. Whatever goes in has to come out. Okay, so in that case, I1 and I3 go into the node, I2 comes out. Next, we can start writing our loops. So for the loop on the left, we start at A. The first thing we go across is the battery. We go from negative terminal to positive terminal, so we pick up a plus V1. We keep going around the loop. The current gets to a resistor, and we lose some voltage here. Now you may say, why do you lose? Well, if you think the positive charges are moving in this direction, well, then the battery is going to sap their energy away, right? Another way to think of it is, look, okay, if a bunch of charges crash into this side of the resistor, then it'll leave that side of the resistor positively charged and this side of the resistor negatively charged. And then since we're going from positive to negative, you pick up a minus sign, okay? Notice on the other hand, here the current goes upward, and so you end up with a bunch of plus signs here and a bunch of minus signs here. And as we work our way around the loop, we encounter the minuses first, and we go from negative to positive. So that's why there's a plus sign here. So I put the currents the way I did just to really highlight the idea that the direction your current goes is different than the direction your loop goes. So your loop will continue clockwise, and it may encounter currents going in the same direction or currents going in the opposite direction. But you always want to pick the directions of your currents first and leave them fixed while you're doing your work, okay? So if your loop goes with the current, you get a minus sign. If it goes against the current, you get a plus sign, okay? Let's do the right loop. So for the right loop, it's the same thing. We start at B. We go from negative to positive. We cross the resistor going with the current, so there's like a bunch of pluses here, a bunch of minuses here. That's why there's a minus sign. And then we keep going, same deal, pluses here, minuses over here. And so you get another minus sign, okay? And then that's that. And believe it or not, that's it. That's pretty much the whole problem. The rest is algebra, which you are probably as good at as I am. I wrote it here. I'm not really going to talk about it much other than to say that using the values up top, I got it that. If you want, you can pause the video and make sure I didn't cheat or make a mistake. What can we do with that, though? Once we have those currents, okay, then the question says find the power. Okay, fine. So the power by each battery, there's a 5-volt battery and a 10-volt battery. Okay, so power is IV, the current that is associated with each battery. So this guy is 1 times 5, so 5 watts. Okay, and then the current from battery 2 is I2. That's the current in the branch with this battery, I2 times 10, which is 0.5 times, 1.5 times 10. So that's 15 watts. And notice that they add up to 20 watts. Another way we could have figured this out, though, is we could have said, look, there's power being dissipated by these resistors. Who's generating the power that those resistors dissipate? The batteries. So if we add up all the power from the resistors, so for each resistor, it's I squared R, I squared R, I squared R. And we can punch that up. If you work out the power dissipated by each resistor and you add it all up, you'll find out it also equals 20 watts. As it should. You can't generate power from nothing. So the batteries supply 20 watts. The resistors eat 20 watts. Okay, hopefully this was more helpful than confusing.